Hello friends, in this video I'd like to solve the following problem from the Romanian District Mathematical Olympiad for 12th graders, year 2000, problem number 4. Let f be a function from the interval, compact interval 0, 1 into r. Let it be a Riemann-integrable function. We wish to compute the following limit. Limit of sum going from k equals 1 to n of e to the power 1 over n f of k over n minus n, limit as n goes to infinity. So it's a very nice problem. Here are my hints. First, since our function f is Riemann integrable, notice that this sum of f of k over n, it converges as n becomes larger and larger. It converges actually to the integral of our function. Also, recall that every Riemann-integrable function is bounded. So in particular, our function f is bounded by some negative number m, capital M. A crucial part, you should introduce this sum and show that sum from k equals 1 to n of e to the power f of kn over n minus this second sum, it converges to 0 as n goes to infinity. And to do that, since we have the exponential function right here, recall that it has a nice Taylor series representation. E to the power of x can be written as series going from j equals 0 to infinity, x to the power of j over j factorial. Combine this together and you will get your result. So give this problem a try and I will see you in just a minute. Alright, so you know what, let's start with exactly this sum, which I have written right here in yellow. Let's start with this sum. I wish to show that as n goes to infinity, this sum converges to 0. And let's maybe also make absolute value right here. What can we do about it? Well, let's take a look. First sum stay as it is. And notice that, maybe I will do it in one go. Notice that this number n can be represented as sum over ones, yes? So we can write our sum as k goes from 1 to n, e to the power f of k over n minus 1 minus f of k over n, close the absolute value. Right, but now, by the triangle inequality, absolute value of sum is less than or equal the sum of absolute values. Minus 1 minus f of k over n. Right. And now, what I wish to do is to take this part right here and expand it using Taylor series. So we have the following right now. Horrible sigma. Sum going from k equals 1 to n of, and this part written in pink can be written as series going from 0 plus infinity of what exactly? 1 over j factorial f of k over n to the power of j minus 1 minus f of k over n. Perfect. Now, I wish to separate first two terms of this pink sum. Because notice that if I separate terms with j equals 0 and 1, if j equals 0, I have 1. If j equals 1, I have plus f of k over n. Then I have the rest of my sum going from 2 to infinity. 1 over j factorial f of k over n to the power of j. Also, I'm running out of space, so maybe, oh, no, finish it right here. Right. And now 1 minus 1, f of k over n over n, f of k over n over n. Simplifies. Alright, so it's, and now I will make use of triangle inequality once again. Triangle inequality. Triangle inequality once again. And I have series from 1 to n. Series from j equals 2 to infinity. The absolute value of 1 over j factorial f of, maybe let's write it this way, 1 over j factorial f of k over n. Here we have absolute value to the power of j and to the power of j, which is perfect. Now, since f is Riemann-integrable, since f is Riemann-integrable, it is also bounded. I.e., there is a constant m which is greater than or equal 0, such that f of x, absolute value of f of x, is less than or equal m for all x between 0 and 1. Alright. And now, what I will do now is to use it to go further with my chain of inequalities. This means that our sum is bounded from above by this 1 over j factorial m to the power of j over n to the power of j. Alright. And also, maybe I will do one more thing. Or maybe not. Now, let's take a look. K is gone. So we have this sum can be replaced just by n. So it's n times our pink sum. 1 over j factorial. And also, maybe, I will do the following trick. I will take n from the denominator, and I am left with m to the power of j, n to the power j minus 1. Alright, here we have actually equality. Or maybe, you know what, I will even take n squared. Because I can. Right. And now, finally, after all of that, we have 1 over n times this sum going from 2 to infinity, 1 over j factorial, m to the power of j, n to the power j minus 2. And notice that this part right here, well, it's some number. It can be computed. It's some function of f of n. It can be expressed using exponential function, but whatever. And notice that f of n, this function, maybe not f of n because it was already used, it's g of n. Notice that this is of course greater than or equal 0, and of course g is decreasing. It's decreasing as n increases. How do I know it? Well, because we will have greater and greater denominators. So it should be pretty clear that this entire thing converges to 0 as n goes to infinity, because this converges to 0, and this is some non-negative decreasing function. So the whole thing goes to 0. It goes to 0. Which means, remember that all of that was just upper bound of this sum. So since this converges to 0, this sum which we have right here also converges to 0. Let me copy it real quick. So all of this converges to 0 as n goes to plus infinity. Now let's take a look at this sum which I introduced. So notice that since f is Riemann-integrable, this sum, just this sum, as k goes from 1 to n, f of k over n, it converges at n, as n goes to infinity, it converges to the integral, Riemann integral of f of x dx. How do I know it? Well, if you think about how Riemann integral is constructed, to compute Riemann integral, for example, we have interval 0, 1. If you have some function, you are partitioning this interval 0, 1 into smaller and smaller pieces, and you are taking some values in these intervals. Yes, so for example, I'm partitioning 0, 1, let's say in equal pieces of length 1 over n. 1 over n, 1 over n, 1 over n, and so on. All right, and once you do it, you can take any value inside these smaller intervals. For example, we can take upper values from the right side. For example, this value right here is f of 1 over n. Then this value right here is f of 2 over n, and so on. And to compute a Riemann integral, you are taking this length of intervals and you multiply by these values. And this is exactly what we are doing here. We are taking some values and we are multiplying by the length of the interval, 1 over n. It's division by n. And as you take n to infinity, this approximation of the area under the curve becomes exactly the Riemann integral. Alright, and now let's combine all of it and we have our answer. That means that our limit as n goes to infinity of sum going from 1 to n f of k over n minus n, we can split it into two limits. First limit is f of k. Sorry, in our original problem we have exponential function right here. E to the power f of k over n minus n. Here we can introduce this sum, f of k over n, and actually you can add limit as n goes to infinity, as k goes from 1 to n, f of k over n, and now, as we know it, this first limit right here is 0. We have demonstrated it. 0, while the second limit is just the Riemann integral of our function. Which means that our limit equals the Riemann integral from 0 to 1 of f of x dx. And this is our answer. Our limit equals this definite integral. Very nice problem, I'd say. Very nice problem. So thank you very much for watching. I hope that you've learned something new this time, and I will see you next time. Goodbye.